All right, so we're gonna try to finish up equilibrium here. So we've gone through the calculations. Hopefully you are clear on those. And so now we're gonna get into just a couple more concepts, things we need to cover related to equilibrium. So the first thing is the reaction quotient. So reaction quotient is Q. It's written the same way as your equilibrium constant K, except we're not plugging in equilibrium values. So Q and K are going to be written the same way. To calculate the value for Q, you substitute in the initial concentration of your reactants and products into the expression. So when we look at, there's a difference between Q and K. They're written the same way. So we do products divided by reactants, the concentration raised to a certain power. And one thing to note, it could be concentration, it could also be pressure. And so if we take a second, we can go here. Let's see, let's go to a new screen. So if we go here, and we look at K and we look at Q. So we have, if we're looking at this, you have your equilibrium constant expression, KEQ. And in that, you could have Kc, which would just be in terms of concentration. You could have Kp, which we would do in terms of pressure. So remember that pressure is used when we have gases. So we can use that for gases. And remember when we plug into, so our equilibrium constant, the only thing we're plugging in here would be things that are gases or aqueous. All right, and so our expression is K is the concentration of products divided by the concentration of reactants, and I'll just put X and Y because we know we raise them to a power, and that power is the coefficient. So Q, the reaction quotient, so Q would be the same thing. Q is the concentration of your products raised to a power divided by the concentration of your reactants raised to a power. So if we were to write the expression is exactly the same. The difference between K and Q lies in what numbers are you plugging in to calculate. So here we have to plug in numbers at equilibrium. That's what we've been doing, right? We've had to find at equilibrium, we had to find what those are and plug those in. Here, we're going to plug in numbers. I'll put at beginning. So beginning of the experiment, or really we're plugging in those initial concentration values. So don't let this confuse you too much, K and Q. They're very similar, except the only difference is coming in what numbers are you plugging in. It's still looking at a ratio of products to reactants. So we're still comparing products to reactants. So again, your equilibrium constant, KEQ, that's kind of like our generic term. And then we can get more specific within those, the KEQ, KC, and KP, just in turn, are you plugging in concentration values or are you plugging in pressure values? And so then we can go back. We can go back here. Again, we're plugging in those the concentration values. And so the importance here of K and Q is we can compare K to Q. And so we have to know if Q, how they compare and how they relate to each other. So if we're given a problem and Q is equal to K, that means those numbers we plugged in to Q, those are actually equilibrium values. So if Q equals K, we know we're at equilibrium. If Q is bigger than K, so if Q is bigger than K, there's too much product. So think back to your expression, it's product over reactant. So if that number is bigger, that means the numerator is too big. That means the product is too big. So the first thing, if Q is greater than K, we know there's too much product. And products are on the right. So we know that the equilibrium is going to shift left to then get back to being balanced out. If Q is less than K, that means the denominator is too big or the amount of reactants is too big. So that means there's too much reactant. So the reaction is going to shift right, or it's going to make more product in order for us to be back at equilibrium. So understand Q is the same expression as K. We just plug in different values. And then, so pretty much Q is you're plugging in values not at equilibrium. And then that's going to be able to tell us which direction is the reaction going to shift in order to make what we need to get back to equilibrium. So, and then know how to write the expression, how to plug numbers in, but then understand if Q is equal to, less than, or greater than K, the implications that has. Le Chatelier's principle is something that you covered in honors chemistry. We'll cover it here. This is, you can write this down, whatever, but this is a kind of a not super complicated definition, but if we have a system at equilibrium and you disturb it. So first thing, how can we disturb equilibrium? We can change temperature, we can change pressure, we can change concentration. If you do that, the equilibrium, the reaction is going to shift one way to compensate for that disturbance. So that's Le Chatelier's principle. Your body right now is at equilibrium, right? We call that homeostasis. When you exercise, you take your body out of equilibrium. And so your body is smart, though. It's going to shift back. It's going to take measures and precautions to get you back to equilibrium. Because if you get too far outside homeostasis, you're going to die. So that's one example we can look at. So these reactions, if you have a reaction that's at equilibrium, it will stay at equilibrium until it's disturbed. Again, the three ways we can disturb it are temperature, pressure, and concentration. Oh, let's go back for a second. So here, the Haber process, we're looking at using N2 and H2 to make NH3. It's important in fertilizers. And so if H2 is added to the system, N2 will be consumed and the two reagents will form more NH3. So if we look at this, if you add H2 is on the left. If I add H2 to this, it's gonna, so we're at equilibrium, which there's no double-sided arrow here, but this is an equilibrium reaction. If we were to add N2, that gives us too much stuff on the left. So then the reaction is gonna shift to the right in order to make more of what we need on the right. So if let's do this, let's go here. Let's go back here and let's kind of look at that scenario. So if we're looking at that reaction, so that reaction was doing N2 plus H2 gives us NH3, and we can balance that like so. Now, there's three different things that we can look at that will disturb equilibrium. And so these are all gases. And so we can look at temperature. That would cause it to be disturbed. Concentration and pressure. And so we'll look at those real quick just so you can understand how we're supposed to describe these changes. And so we can look at concentration first. So again, remember, concentration, you're just looking at how much of something you have. And so we could look at, there's a ton of scenarios we can look at. So we could look at increasing the concentration of N2, which that just means we're going to add N2. So we have to know what happens. So what would happen here if I added N2? Well, if we add to the left, we have too much here, so it's got to shift to the right in order to get back to equilibrium. So we would say shift right. Now, the same thing here, if I increase the concentration of H2, or if we add H2 in, what's going to happen? Well, H2 is on the left. I've got too much on the left, so I'm going to shift right in order to get back to equilibrium. And so we would say shift right. And then you could also increase the concentration of NH3. Now, NH3 is on the right. So if I add NH3 to this, that's too much on the right. So we're going to shift left. And so this would be a shift left. And so understand in all three of these scenarios, we are adding. I'm adding N2, I'm adding H2, I'm adding NH3. I would write this down. So what does a shift right and what does a shift left, what does that mean? So shift right means make more product, right? Products on the right. Shift left means make more reactant. If you want to make more product, you have to use reactant. And if you want to make more reactant, you have to use product. So just understand what shift left and shift right means. So if we were to decrease the concentration of N2 or decrease the concentration of H2 or decrease the concentration of NH3, take a second and see if you can tell me how would that shift the equilibrium. So if you want to pause it, you can pause it. And is it going to shift it left or is it going to shift it right? So take a second and see if you can do that. And so we know, so N2, if I remove N2, N2 is on the left. So that means I don't have enough of what's on the left. So I'm going to have to make more of what's on the left. And so that means shift left. And that would be the same scenario with H2. With NH3, if I remove NH3, that means I have not enough here. So that means I need to make more of what's on the right. So make more what's on the right, we're going to shift right. And so we look here, and I could say that's removing. So we can look here. One thing, so general statement, if we're adding, what's going to happen? We're going to shift to opposite side to which we added. Okay. What happens when we remove something? Well, when we remove something, we're going to shift to the same side. So in general, right, I would make sure you know that. Those are stars. Whatever. So if we add, we're going to shift to the upside. If we take away or remove, we're going to shift to the same side. Again, it's all about being at equilibrium. And then how is your reaction going to shift to compensate for that disturbance? So concentration is one way we can disturb equilibrium. Another way we can disturb equilibrium, let's go to pressure. Now, remember, pressure is just another way to look at the concentration of a gas. And so when we look here, we're looking at a reaction with gases. And so there's two things we can do to pressure. We can increase the pressure or we can decrease the pressure. Now I'll write down the explanations and then we'll kind of explain them. So if you increase the pressure, we're going to shift to the side with fewer gas molecules. If I decrease the pressure, I'm going to shift to the side with more. So when we look here, so I think of it this way. If I were to increase the pressure, let's say we have a balloon. If I were to increase the pressure on a balloon, right, we're compressing it, we shrink it down, we make it smaller. If it's getting smaller, that means I have less space to hold a gas. So that's why we shift to the side with fewer, because it's a smaller area, less gas molecules can fit. So we shift to the side with fewer gas molecules. If I were to decrease the pressure, right, put in a vacuum, that allows it to expand. The space gets bigger, and as the space gets bigger, I can fit more gas molecules in a bigger space, and that's why we would shift to the side with more. So that's kind of how I think of pressure and how to justify it. And so when you look at your reaction here, you have to count the number of gas molecules. On the left, I have 1 plus 3. So if we look at our reaction, I have 4 gas molecules on the left, and I have 2 gas molecules on the right. So here, if I were to increase pressure, we're going to shift right because there's fewer gas molecules on the right. If I were to decrease the pressure, we're going to shift left because there's more gas molecules on the left. Again, it's going back to counting how many gas molecules do we have on each side. So concentration and pressure are 2 ways. Now, let's look at one thing. If you don't have any gases, so let's say they're all aqueous or they're a mixture of solids, liquids, aqueous. If there's no gases, then pressure, a change in pressure does not shift equilibrium. So you could say there's no shift. If the number of gas molecules were the same on both sides, so if it's 2 and 2 or 4 and 4, whatever, if they're the same, then there's not going to be a shift either, right? If they're both the same, there's neither side has more or less, so then we would say there's no shift. And then the last one we can look at is temperature. And so I'll write our reaction here again into plus H2, just so we have it down here. I don't want to zoom out too much to where we can't see it. The big thing is you have to know where heat is for this reaction. Is this an endothermic or exothermic reaction? So if it was an endothermic reaction, heat's going in, we would know heat would have to be a reactant. If it's an exothermic reaction, we would know that heat would be produced or heat would be released. So that's the first thing you have to know. And so here, I will tell you that this is an exothermic reaction. This releases energy. And so now when we, because remember temperature and heat are related, right? Higher temperature, more heat. And so here, if I'm looking at this scenario, then we just look at if I increase the temperature or if I decrease the temperature. How do we increase the temperature? We have to add heat. How do I decrease the temperature? We have to remove heat. And so how would that shift it? Well, now that you know what side heat is on, we just go back to this idea right here. If we add, we shift to the opposite side. If we remove, we shift to the same. So if I were to increase the temperature here, I'm going to add heat to the right, so I'm going to shift to the left. If I add heat, if I remove heat, right, I remove from the right, I'm going to shift to the right. So the big thing with temperature is you've got to find out endothermic or exothermic. And from there, that will tell you which side of the arrow you put heat on, whether it's a reactant or a product. And then after that, you just go back to how we started concentration. Are we adding or are we removing? And so with, AP, you're going to get, if you get a reaction at equilibrium, you're going to have to know if we add this, if we take this away, if I change the pressure, if I change the temperature, is it going to shift left? Is it going to shift right? So if you need to go back and rewatch this just to make sure you understand it, I would recommend that. So that's Le Chatelier's principle for us. So if we jump back real quick to the PowerPoint, we got Le Chatelier's principle, we got through here. We look here, what can change? And so we know temperature. And so here, if we were in class, we would actually do this lab. And you would see as we put in hot and cold water, it would turn from dark blue to purple, because that's just an example of equilibrium. Looking here, so again, you have one gas on the right, none on the left. So again, you could look at pressure. One thing they note here is volume. You may see this in questions, they change the volume. Understand if you change the volume, you're inherently changing the pressure. Volume is just, am I making the container bigger or smaller, right? And as the container gets bigger, pressure goes down. As the container gets smaller, pressure goes up. So just make note of that, you could change the volume, but that just relates back to a change in pressure. And last thing about a catalyst, so understand this, catalysts, they do not change anything about the amount you have at equilibrium. The only thing is you will reach equilibrium faster. So a catalyst increases the rate of the forward and the reverse process, both. So again, that hump is going down, the activation energy is going down. Excuse me. But know that a catalyst, the only thing it changes is that we will get to equilibrium faster, but it won't change the concentrations that we have at equilibrium. So when you achieve it faster, but the equilibrium composition remains unaltered. So again, the only thing that a catalyst does related to equilibrium is that we get to equilibrium quicker. And that's it.